Okay, so before we go any further, what I want to do is I want to talk about the importance of the central limit theorem as it relates to your role, your job as a data analyst or a data scientist. So with that being said, we're gonna go ahead, jump right in. We're gonna start with looking at central limit theorem, and I'm going to start by pointing out that the central limit theorem, it has two very important parts to it. One, the first thing is that random samples, they eventually fall towards a mean with central limit theorem. That's the first part of central limit theorem that's important. The second part is that sample values of a sufficient size, they can provide insights about the larger population. Now, I'm going to go back to those 2 points later. They're super important, but for now, just understand that those are the 2 parts of the central limit theorem. That if you take random samples, and I'm assuming that all the samples have an equal chance of being selected, then they all will fall towards that same average. And the second is that if you understand what's going on at a small level, with the subsample of your data set, then you can have insights about the overall data set, about the general population. But central limit theorem is important to us for 2 reasons. The central limit theorem, it's used by data analysts and data scientists to perform what we call hypothesis testing. And analysts and data scientists, they use central limit theorem to infer population characteristics from the sample. And so the first reason why it's important is hypothesis testing. Hypothesis testing, that's used to check if a hypothesis is true or not. For example, I could say, I could have 2 columns of data. One column of data is related to whether someone's a smoker or not. And the other column of data could have something to do with cancer probability. What I can do is I can use central limit theorem, look at those columns of data, and from that, just from a small subpopulation, I can develop insights about the association of cancer, for instance, to cancer, the association of smoking with cancer risk, for instance. Or I can do things like check to see if going to the gym helps in weight loss. Or I can do things like seeing if the COVID vaccine is helpful with respect to COVID-19 symptoms, or whether somebody new to the organization is likely to leave within a couple of years. Now, to get this knowledge, I don't have to go through the entire population to get this knowledge. I just need to have a sample of that. So I can use hypothesis testing. Those are my hypotheses that I just listed there. Going to the gym, helping with weight loss, that's a hypothesis. COVID-19 vaccinations, helping with COVID symptoms, those are all hypotheses. The second thing is inferential statistics. So let's say, imagine that you're a data analyst or a data scientist and you want to find the average income of people in Miami-Dade County. How would you go about it? Miami-Dade County is too large. There's several million people in Miami-Dade County, so it's not possible to capture the income of every individual person in Miami-Dade County to find the average income. So what you can do is you can capture the income of, say, 500 or 5,000 people in Miami-Dade County, find their average income, and then from that you can infer the average income of everybody in Miami-Dade County. So you as an analyst, you can find the population average, the financial average by calculating the average income from the normal distribution. So those are the 2 reasons why it's important. And remember, as a data analyst, your job is to find insights from the data so that you can provide the business with actionable insights. Central limit theorem is super important with respect to that. Okay, so here's the thing. Let's go back to the two parts of central limit theorem. The first part says central limit theorem states that if we take a repeated random sample from a population and calculate the average of each sample, then the distribution of those sample averages will be approximately normally distributed, even if the population the samples came from is not normal. So let's talk about what that means. And what that means is that if I take, for instance, let's say let's say, for instance, we take employees at not employees, let's say students. Miami-Dade College has, I think, 100,000, 120,000 students. Let's say 100,000 students. If I wanted to find out if the students at Miami-Dade College were satisfied with the quality of their education, what I could do is I could take a random sampling of, say, 1,000 of the 100,000 students, have them do a survey, and for every survey that they fill out, let's say that we have an average satisfaction score. So we would have 1,000 satisfaction scores, one for each person that filled out the survey. What you'll see is that it will generate this bell curve. When I say normally distributed, that's what I'm talking about, is a bell curve. If I just took the averages of the 1,000 students with their satisfaction and I plotted that in a histogram, then you'll see this bell curve start to emerge. We call that, sometimes we'll call it normalized, sometimes we'll call that bell curve a Gaussian distribution, but it's all saying the same thing. That is one of the secrets of nature, so to speak. And here's the thing, this bell curve, it shows up, central limit theorem shows up all over the place, in business, in biology, in economics, in science, of course, finance, everywhere. Central limit theorem shows up everywhere. And the reason that that's important to you is because many of the analytics techniques that we're going to cover is going to assume that the central limit theorem is holding for that data that you're analyzing. If you're a data scientist and you want to put this data into a model so that you can make predictions, most of the models will assume that your data adheres to the central limit theorem. Central limit theorem, it's important. It's germane to everything that we do as a data analyst or as a data scientist. The second thing about the central limit theorem is that it states that the mean of the sampling distribution will be equal to the mean of the population distribution. So that's important for a different reason. That is something that should be, I hope you find that amazing. What that means is that if I wanted to find out something about, let's say, the entire population of the United States, I don't have to go to everybody in the United States. I can just get a sampling of that. If there's an election that's occurring in your state, I live in Florida, I don't need to go and ask everybody in the state of Florida how they're going to vote. All I need to do is to get a subsample, a percentage, 1,000, 3,000, a few thousand people, make sure that I have a good random sampling. So I'm not just pulling everybody in Miami City or pulling everybody in Tallahassee, but I have a good random sampling where everybody in the state that's an eligible voter has an equal chance of being selected. I get 2,000, 3,000, 5,000 people. You'll see a trend start to emerge. The shape, if I did a count plot, would be in the form of a bell curve, but I can transfer that knowledge. I can infer that based on that subsample, that is how the whole population in the state of Florida, that's how they feel. That's how the polls work. It's amazing. I can study a subsample. And here's the thing. Usually it takes about 30 samples before you start to see the effects of central limit theorem. It's useful. It's useful because using a sample mean because we can draw conclusions about the larger population. This is a deeply insightful nugget, and it's the cornerstone of data analytics and data science. I can give you examples where economists will use the central limit theorem to find the average annual income of people. I can give you examples where biologists will say, hey, I want to find out what is the average height of, say, the royal palm tree in Miami. And so they go out and they measure 30 royal palm trees. And based off of that, they know the average height of royal palm trees in all of Miami. I can give you examples in industry and manufacturing where a manager will say, hey, we're manufacturing stuff. I want you to give me 100 products. And the manager will look through those 100 products. If they find 4 of those 100 have defects, then that manager knows that that knowledge transfers to the overall population, because that means that you have a 4% defect rate. That knowledge, it transfers. Surveys. I, at this point in time anyway, am a new employee at Miami-Dade College. I'm a new faculty member here. The HR department sent me a survey. And the survey went to all new employees. It was a satisfaction survey. I filled out the survey, me, as well as a percentage of all new employees. And so the college now understands my satisfaction, or the satisfaction of all new employees, based upon the sample, the people that filled out the survey. If you're a farmer, an agricultural scientist, you might want to test a new fertilizer. You roll that fertilizer out on 15 different fields, and you measure the average crop yield of every field. If you find that the average field produces 400 pounds of corn or wheat or barley or whatever, then your best guess for the average crop yield for all fields will also be 400 pounds of barley, wheat, corn, whatever. The central limit theorem, in conclusion, is useful because we use that to study a subset of the data and draw conclusions about the larger population mean. That is why it is deeply insightful, and that is why the central limit theorem is effectively the cornerstone. That's why it's the cornerstone of data analytics and data science. So let me share my screen and give you a quick demo. Okay, let me full mode here. Okay, so from here, what I'm going to do is I'm going to ask you to assume that this is day one. Assume that, I like to use the analogy, assume that you are a fisherman. And every day you catch, as a fisherman, you catch 5 fish. And then you measure the length of all 5 fish. All 5 fish come from the same population of fish, so they're not different fish. And the fish are all between 1 and 20 inches. Okay, so I'm going to copy this. And I'm going to put this random equation in all fish 1, 2, 3, 4, 5. And then what I'm going to do is I'm going to pull the average. I'm going to pull the average from these columns here, 1 through 5. Okay, let me close this out. So on day 1, for instance, the first fish I catch is 16 inches, the second is 7 inches, 13 inches, 4 and 5. So that means the average length of the fish that I caught is 9 inches. On day 2, and I'm going to do day 2 as a 2 plus 1. So the next day, and I realize that my random numbers changed. Okay. Actually, I should have did this for all of them. I don't know why I always do that. I'm going to do Control D as in David to go down. Okay, so next day, you can see the average length of the fish is 11.6 inches. If I do this here, I'm going to go down to 11. Do Control D. And now what I'm going to do is I'm going to go to column G, which is the average. Now, I don't know the size of every fish in the sea of this type, but I know for 10 days, I caught 5 fish a day, and these were the average, this is the average length of these fish. So I'm going to go to Insert, and I'm going to insert a histogram. And you can see that this histogram after 10 days doesn't give me a lot of data. So fish between, it looks like 6 inches and 10.4 inches. That's about how many were in that range. And between 10.4 and 14.8, that's how many fish were in that range. Okay. So these are the 10 values that we had. This was the average 6 times, and this was the average 4 times. Okay, just the average. All right, so there's not much information there. But like I said, it takes about 30 data points. So let's go down to 30. Sometimes it could be a little more. I'm going to do Control D to go down. Now I'm going to take the average column. I'm going to do an insert. And I'm going to insert a histogram again. And look at that there. Now you see the beginnings of the central limit theorem. These are random equations that I put into Excel. A fisherman doesn't get to pick what fish they catch. The fish decide if they're going to, and I'm assuming this is rod and reel, the fish decide if they're going to go for the bait. It's miraculous. The central limit theorem is alive and well here. So for 8 days, the average fish were between 8 and 10.3 inches. For 15 days, the average length of a fish was between 10.3 and 12.6 inches, etc., etc. But notice that it's starting to collapse towards a mean. And don't forget the big picture in this. Don't forget the big picture. The big picture is that all I'm doing is I am taking a sampling of the fish. Not all fish, just a sampling of the fish. And you see the central limit theorem start to show up. So let's now go from 30. I'll make this quick here. From 30, let's go to, let's say, 365. So here would be 366. Okay. So that would be Control D. So let's see what happens after a full year. I'm going to get the average. I'm going to insert a histogram, and now we really start to see, this is 1 year averages. Now we really start to see a normal distribution, a Gaussian distribution, a bell curve. This applies to everything. This applies if students are taking tests. This applies to the speeds that people go on certain roads. This applies to stocks. It applies to business sales, everything. You see this over and over and over. And just to go crazy here, that was 1 year. You can see we're collapsing towards a mean. We're going to between 1 and 20, so it's no surprise that the average is hovering at about 10. And so what I can infer is that the average size of a fish is going to be about 10. It's going to be about in the middle of that distribution. So I'm just going to go crazy here and just put a couple thousand. Say that this fisherman fishes every day for 4,210 days. One extra day there for the label. Let me do Control D. Okay, so this fisherman fishes every day for 4,200 days in a row. The amazing thing about central limit theorem, if I do insert the histogram, you start to see that the signal continues to shine through. The signal continues to shine through. Now, if you did this, yours would look slightly different, but the pattern, the shape will be identical. It will be the exact same thing. These are the averages after 4,200 and, I don't know, 10 days, I think, something like that. So now I can start to infer facts about the overall population of fish. I can look at this here and see that over here in the mean, about 10, somewhere around here, somewhere at about 10, the average size of a fish is going to be about 10 inches for this fisherman. I could then go to the fisherman and say, I bet you that you've caught fish that are 18 or 19 inches, but you've only rarely caught those fish. I can go to that fisherman and say, I bet that you've caught fish of this species, of this type, that were 2 inches, but I bet that that has rarely happened, assuming these are all adults, of course. I can then go back and I can find the average size of the fish, and I can say, this is going to be the standard deviation on either side. So I know that 70% of the fish that you caught are between, just making this number up because I hadn't calculated the standard deviation, between 7 inches and 13 inches. 70% roughly of the fish that you caught were in that size. That's normal. But there's a lot of facts and insights that I can pull from this data. Central limit theorem is something that every data analyst, every data scientist should know. Anyway, we will start to use that as the foundation to analyze columns of data as we move forward. I hope you found some value in this, and we'll continue on in the next section. Thank you.